Let's look at some exam questions involving DC motors. We've got a figure showing the 4 positions A, B, C and D of a coil in a DC motor. The coil can be assumed to be a single wire, that's important to note, which is in a uniform magnetic field parallel to the coil when in the orientation shown in A. So we can see here's the magnetic field and we're told it's uniform and it's parallel to the coil here. It rotates in the direction as indicated, so we can see this little arrow here, about the axis which passes through the middle of the sides LM and NK. The coil is attached to a commutator. Now these days we would have to specify split ring commutator specifically, not enough to say commutator, to which current is passed by brushes which are not shown in the figure. So we don't have the brushes that we often see, sometimes sort of drawn a bit two-dimensionally there, which then connect it to the external circuit or a cell or whatever we've got going on there. So first off, it says, when the coil is shown in position A above, in which direction is the current flowing in the side KL? Okay, so we don't have a direction of the force, but we can see that the motor is rotating in this direction because it's annotated on the diagram. So if we're looking specifically at side KL, in order to achieve that rotation, it must have had a force upwards. Now let's apply our right-hand slap rule. And it says explain your answers. So let's apply the rule and also write down what we're doing. To achieve this rotation, force on KL is up. Therefore, due to right hand slap rule, so whenever we're applying one of our right hand rules, it's really good, I was going to say rule of thumb, well that does work, it's really good to number 1 identify the rule, we've just said the right hand slap rule, and we're going to go ahead and talk about what the fingers and the palm and the thumb represent. Usually we'd talk about the fingers, the thumb, and then the palm would be the result, but here the thumb is the direction of the current, which is what is the unknown in this question here. So this is how I like to go about this. So I would say fingers, they're representing the B field, which is the magnetic field, and specifically in this question they're pointing to right. So point to right. Don't know why I capitalized right, but it must have been very important. This is very important. You cannot just say fingers are the B field. You've got to always specify the actual direction in the question. So the next thing we've got is little dot points. Palm, that's the force, and we identified due to that turning effect it was up on KL. So again, needed this bit of information here, not enough to just say palm is force, because you could have just copied that from your note sheet. It's important to specify where it is in the question. And therefore, thumb, which represents the current, and we could try and talk about into the page or out of the page, but because they've got labels of L and K here, we can actually say that. So let's do what we've said so far. Fingers are the B field pointing to the right, so point your right hand to the right. The palm, which is the force, needs to be upwards on KL. So hopefully you're holding your right hand with palm facing upwards right now. If you do that, you'll notice that the current, the thumb, needs to be going from K to L. So using the notation that's given in the question can be handy here. So we can note that there. So we've specified the current is flowing in this direction inside KL. We've explained our answer, all good to go. Next part. Side KL of the coil is 0.10 meters long, and we're told the magnetic force is 0.6 newtons, and that's acting upon it. If the magnetic field has a magnitude of 1.5 Tesla, that's B, what is the magnitude of the current in the coil? So the equation that relates together the unknowns of what we need is F equals NBIL. Recall I said sometimes people just write F equals BIL, but I think it's a really good idea to get into the habit of writing N, even if this case, they said it was a single wire where N is 1. It's really going to pay dividends if you have multiple coils of wire. So we are interested in finding the current. I often write it with the I with those little things there, so it doesn't look like I'm saying 1 equals. We're going to take that F and we need to divide it by N, B, and L. Okay. So the force was 0.60, N we said was 1, still good to show that, B was 1.5 Tesla, and we had the length was 0.10 meters. Everything's in appropriate units of meters, newtons, that kind of thing. So calculating this, I get 4, and let's do 2 sig figs, 4.0 amps. Not newtons. Okay, let's continue. Consider 2 cases. The coil is at rest in the orientation shown in diagram A above, and the coil is at rest in the orientation shown in diagram B above. We're going to explain what would happen in each case. If current is allowed to flow in the coil, your answer should discuss the forces on each side of the coil and their net effect. Okay, so let's have a little looky-loo. Now with this question here, they specified that the current was allowed to flow in the coil. So because we don't have any location of brushes and we don't know where it's going to be at the split, and as I said, they specifically said current is allowed in the coil, so we're not going to be looking at a situation where there is no current. It says we wanted to discuss the forces on each side. So we were interested in, let's get rid of this, it was diagram A and diagram B. So before, we saw we had a force acting this way and a force acting this way. Didn't really need to erase that previous arrow. And that would have led to a turning effect here. So as a bit of a reminder, we had the current. That was the charges were traveling from K to L. And we're going to assume that we're going to have the same thing going on here, that the current's going to still be traveling from K to L. Again, it said that we're assuming that current is traveling around this coil. So that's the only information we have to work with. So in that case, if we apply our right-hand slap rule, we're going to have a force upwards again on KL and force downwards on MN. And that's not going to be able to produce a turning force at all because we've got 0 torque going on there. The forces are not always going to be trying to expand out the ring like that. It depends on the orientation of the magnetic field and the orientation of the current through it. So let's go back to that question. And let's talk about what happens in either case. So force on LK, that was up on that side, and it was down on the other side, which we'll say was NM, if we go back and have a look. So let's put as force is applied at a distance from the turning axis, a torque, and the symbol for that was this Greek letter. Can't remember its name all of a sudden. A torque is applied and the coil begins to turn. In option B, we still had those forces being applied. So forces applied as above. However, the force is parallel to that R, and we can treat R as that line that goes from the center of rotation or the axle or the axis of rotation to the location where the force is being applied. Torque equals 0, therefore motor doesn't turn. So it would be unfortunate if you tried to get your motor turning in this situation by having it in the location that we had in B there. What you need to do is you need to give it a little bit of a push. And we did a prac the other day where we also had some other forces at play, but if we imagine that they were negligible, the location of the coil initially matters a lot. So we had to give it a little bit of a push, not just to get going and overcome friction, but also to ensure that it's in a location where a torque can be applied. Same as if you were trying to open a door, much better to apply a force perpendicular to that radius, the distance from that hinge to where you're pushing on the door, then trying to apply a force parallel to that line. Much more effective at turning. Okay, another question. We've got a single loop, so that tells us n equals 1 again, and it's in a uniform magnetic field. The loop can rotate as shown in 3 different orientations. In each case, there is a current flowing around the coil from W to X to Y to Z. So it's going in this direction, which is labelled as a little arrow on each of those diagrams there. We're told the magnetic field B is 0.10 Tesla, and we have the current in the loop is 0.30 amps. With the loop in orientation A on the figure above, what is the magnitude of the force acting on side XY of the coil? And we're told the length of WX as well. Now you may be a little alarmed because we don't have the side length xy. However, if we pause and consider the magnetic field and the direction of the current, you'll see that it doesn't actually matter. This orientation is a little different. We're used to seeing this more in a horizontal kind of plane, but here we have the magnets above and underneath the loop. And remember, the magnetic field needs to be coming out from the north and going into the south. So I'll just draw a couple of field lines here. In this instance, we can see that the current traveling from X to Y, let's draw that in a different color. So this will be the current that is parallel to the magnetic field. And because it's parallel to the magnetic field, we have no force acting here. So I in, let's say current from X to Y is parallel to B field. Therefore, F equals 0. Now, you might be the kind of person who prefers to, rather than thinking about parallel and perpendicular, you might like to think about this equation. So I'm going to put a little or here. You might like to do F equals NBIL sine theta. And as theta equals 0, F equals 0. So with that situation, current and magnetic field are parallel to each other, so there's no force on side xy. So that means we're not too alarmed by the fact that they haven't given us a length. Now I do suspect in part B, we might need to do a calculation, maybe not. In the figure below, the arrows indicate possible directions of the force on side WX now of the loop in 3 orientations A, B, and C. The arrows in each orientation are in a plane perpendicular to the axis of rotation of the loop. Okay. For each orientation, circle the head of the arrow that best represents the direction of the magnetic force on side WX of the coil. If there's no force on this side, write NF under the diagram. Okay. So let's, just for our reference, put a magnetic field line pointing in this direction, just so that's something that we can tick off our mental list and have something visual to refer to. The current we can see was traveling from W to X in each of these examples. So if you look at every single scenario we have here, we can see that there's no situation where that magnetic field is parallel to WX. In fact, in each of these situations, it is perpendicular to WX. So let's apply our right-hand slap rule. We need our fingers of our right hand pointing downwards, and our thumb is going to be pointing into the page in the direction of WX. In that case, and in every one of these situations, the force, our palm, is going to be in the direction of W. So W is going to be the answer for each of these questions. No situation where there's no force, because we always have that current direction is perpendicular to the magnetic field. So now we've got another one. We're looking at side XY now, and we want to consider which represents the direction of the magnetic force on side XY. So let's put this B field in again, just to have something to refer to. We can see in this situation, XY is parallel to that magnetic field, so we have no force absolutely going on in this direction. Let's put that in black. Now, in this situation, we have the current going from X to Y. It's no longer parallel to that magnetic field. So that means we need to apply a right-hand slap rule to be able to determine the direction. So, fingers of our right hand pointing down, our thumb is now going to point from X to Y. So it's pointing to the right, and that means the force is going to be acting into the page. So in this case, we're going to have this arrow here. Now, I've just realized a silly mistake I've made. I was circling W before. W was referring to our wire, so doesn't matter. I did circle the arrowhead that was associated with that in most of these instances, but there we go, fix that one up. Okay, let's look at another one. We have a 50-turn coil. We have a value of N that's not equal to 1. It's free to rotate about the axis as shown. We've got a loop, it's placed between poles of a magnet. We're told the magnetic field strength, and we're told the current. What is the magnitude of the magnetic force on side JK? And we're told its length when orientated as shown above. So let's check. We've got our magnetic field, comes out of the north, goes into the south. It's definitely not parallel to that current, which is going from JK to K. So let's do the right hand slap rule. Fingers are going to be pointing of our right hand. Fingers will be pointing towards the left. We're going to rotate our thumb so it's pointing into the page. So we're going to have a force acting upwards. Haven't been asked for a direction in this question, so jumped the gun a little bit, but we do definitely have a force. And we can calculate that force now. So F is going to be equal to NBIL. If you like doing sine theta, you'd be substituting in theta is 90, which means sine of 90 will be 1. Then we're going to have N was 50. B, we were told in the question, was 0.040. Current was 1.5. And the length of that, we were told at some point, JK, we're told there, and also told there. So 0.050. Calculating that, double check I get the correct amount. I get 0.15 newtons there. Then it says, what is the magnitude of the magnetic force on side KL when orientated as shown? Okay, magnetic field hasn't changed, but we need to look at side KL now. And KL is pointing in this direction. So that means we've got a parallel situation, so we're going to have no force. So we're going to have F equals 0 as I is parallel to B. Perfectly sufficient to write it like that. Students now turn off the current and set the coil at rest, orientated as shown below. They've turned on the current again. What happens to the coil after the current is turned on? Explain your answer. So to know that would be good to find the direction of forces acting. Okay, so magnetic field still pointing from north to south. Let's apply our right hand slap rule over and over really. So we've got, let's look at side JK. Current is going into the page. Magnetic field is pointing to the left, so I get a force pointing up like that. In KL, we've got our fingers pointing still in the same direction, but we're rotating our thumb to point downwards. So now that force, I'm going to try and draw it perspective-wise. It's going into the page. Looking at LM, we've rotated our palm, now it's facing downwards. Our fingers are maintaining that same direction, so force is that way. And we've got this force coming out of the page, which I've tried to draw perspective-wise, not super successfully. That's a little better. Okay, getting into the explanation, the coil will not turn. If we've got forces acting in each of those directions, it can't cause a turning effect. It's really just acting to try and expand the coil. So it says, although forces are applied to each side as shown above, the torque is 0 and the net force on the whole coil is 0. Because we've got forces up and down balancing each other out and into and out of the page balancing each other out. So no torque, no turning effect. So just a little terminology thing I wanted you to be aware of. I've sometimes seen coils being referred to as armatures in exams, and that's, you can see I've just got the diagram. I've just got the definition here, and it talks about the rotating coil or coils of a dynamo, or in this case, we're focusing on electric motors. And sometimes you'll see it talks about the number of turns in a motor, and that's just talking about the number of wires. So that's the value of N that we're considering. Okay, enough for that slight deviation. Let's go back to looking at some of these past exam questions. Okay, we have a schematic diagram of a DC motor, and we're asked which direction will the motor rotate when the switch is closed. So a few things we need to be aware of here. When the switch is closed, how are we going to determine the direction of the current? Well, we're always looking at the direction of conventional current, and that comes out of the positive terminal of the battery. So current will be travelling this way. And that means within the coil, we're going to have the current travelling from J to K, and then from L to M. And we're focusing on those two sides because they're the ones that result in a turning force. Applying a force to those sides results in a torque. So that's going to be the sides of interest. KL, not really of interest because it doesn't help us turn the motor. So we've got the current down pat. Let's also make a note the magnetic field is pointing from the north to the south. Let's maybe look at the force on side JK. Fingers of our right hand pointing to the right. Current is going to be pointing from J to K, sort of into the page. And the force is going to be downwards in this case. So force is downwards, meaning B is the correct direction of rotation. So we have got B, and that's anti-clockwise. So clockwise and anti-clockwise are pretty easy to mix up, especially if you're nervous in an exam. So if you have an analog clock in the exam room, just look up for a moment and you'll be able to see it from there. Okay, part B is asking us to explain our answer, and this is an application of the right-hand slap rule. So I want you to pause for a moment. I want you to think about how you're going to apply the right-hand slap rule, putting together all of the components that we need. It would also be a good idea to note that current is exiting the DC power supply from the positive terminal, because that is again showing demonstration of understanding of physics. So take a moment and I'll pop the answer up in a sec. Okay, so we have an example of a model answer here. So we've mentioned the fact that we know the current, we're talking about it exiting the power supply from the positive terminal. We've specified we're using the right-hand slap rule. We've talked about what each component of the hand relates to in terms of the physics, and we've specified the specifics of the question. You could have similar reasoning, but I would recommend this because it really gives all of the details that the assessors are looking for. And you could also talk about side LM, but then you can say something about the torque produces an anti-clockwise rotation, or these forces produce a torque which allows this rotation. Okay, we've got a pretty famous question to finish us off here, and it's talking about why is the split ring commutator necessary for the motor to operate correctly? Explain the operation of the commutator. One thing that you don't want to really talk about in this style of question is talking about wires getting tangled up. Whilst that is a practicality, a really useful reason to have a commutator, it's not focusing on the physics involved in this situation. Instead, we're going to be looking at the fact that the commutator reverses the direction of the current through the coil every half turn, and we're going to talk about how it does this and how it's connecting the coil to the external power, and why is it important to reverse that current direction? The whole point is to reverse the direction of those forces to maintain a torque. So I'm going to put in the recommended 3-step approach to always get full marks for this question. First off, we need to talk about the fact I was talking specifically about a motor. In the next area of study, there are generators, and they can also use split ring commutators. However, they serve a very, very different function. So you need to be really clear in the question that you're talking about a motor and not something else. So in a motor, we've got here the split ring commutator reverses the direction of the current through the coil every half turn. You could mention that's when the coil reaches a position perpendicular to the magnetic field if you wanted to really go into extra detail if it was like a 4 or 5 mark question. Then a dot point saying it achieves this by alternating the contacts between the coil ends and the external power supply terminals, which swaps the direction of the current. Then, why did we do this? This results in a reversal of the magnetic forces acting on the coil, which maintains a torque. I would specifically refer to torque rather than just continuous rotation because it's a really nice physics word. Now, you notice at the end, it says if it's a 4-mark question, so that response is a really good answer to a 3-marker. If there was a 4th mark, you could say without a commutator, what would happen? Now, don't focus on wires getting tangled up. Instead, talk about the physics. So we could have the coil will oscillate about a position perpendicular to the magnetic field until it comes to a halt in that position. And remember, we talked about in class what would happen if those forces did not change direction to allow for a continuous torque. That's one thing that you could definitely add in if there were more marks available in the question.